These next two pages are to go over something called skeletal structures, at least our first attempt at starting to understand skeletal structures. And skeletal structures are something that you very commonly see when talking about larger molecules. And what I'm showing here is the skeletal structure for prednisone, a steroid. And you can see that there are very few atoms shown. And there are also some sort of lines that don't look familiar, perhaps. And we'll start this with skeletal structures and some basic understanding. We'll finish it in a future week, but I wanted to give you an idea of what we're going for eventually is to be able to understand all of the bonding and all of the intermolecular forces associated with this skeletal structure. Now, skeletal structures, that's our title. And skeletal structures are also called line bond structures. And that's exactly what it's going to appear as a line is a bond. And but the take-home message is going to be that there are a lot of carbon, hydrogen, single bonds and molecules that sort of clutter up Lewis structures and make them more complicated than they need to be, especially for larger molecules. So in skeletal structures or line bond structures, don't draw carbon-hydrogen bonds. And I guess the other main thing as we go through what I'll call skeletal structures is that when you draw a chain or a line of carbon-carbon bonds, you'll draw them so, so draw carbon-carbon-carbon bonds with a bond angle somewhere between 109.5 and 120 degrees. (109.5 to 120 degrees). And we'll talk about why those numbers in a future lecture outline. But let's take a molecule that is sort of big, but not too big, and that's going to be pentane. Pentane has 5 carbons, and each of those 5 carbons, so it's got single bonds between the carbons, and then each carbon has 4 bonds total. So I've got 1 bond to another carbon. That means there are 3 bonds to H's. And that's typical of a carbon that's at the end of a chain of carbons, or a line of carbons. More central carbons have 2 bonds to other carbons and then 2 bonds to H's. And then drawing in all the other H's, we see that pentane has a formula C5H12. And C5H12 fits the pattern CnH2n plus 2, which is the generalized formula, and those are N's, for alkanes. But what we'd like to do is we'd like to draw the skeletal structure where we don't draw the carbon-hydrogen bonds, and we draw carbon-carbon-carbon bonds with a bond angle between 109 and 120, approximately. Nobody's measuring. It's going to go like this. When you put your pen or pencil down, it's 1, 2, 3, 4, 5. Something like that. This is the skeletal line bond structure for pentane. It's got 1, 2, 3, 4, 5 carbons. And it has all those hydrogens, but we're just not showing them. And so it's much simpler. It does show some of the nature of the carbon-carbon-carbon bonds, which again we'll discuss soon. And then it just makes it much easier to think about drawing things like isomers. For example, another isomer would, instead of drawing 5 carbons in a row, and if you remember isomers, so same molecular formula, different bonding pattern, so at least one of these bonds has to be broken, and I'm going to break this one and reattach it in a different place. So I'm going to draw 1, 2, 3, 4 carbons, and this 5th carbon over here, I'm going to attach it in the middle. This is also C5H12, as is this C5H12. And anyway, so starting to think about different molecules, we can prove that this is C5H12 because it has 5 carbons and all the carbons are connected by single bonds. It must, but each carbon, let's fill it in, and I'll draw it approximately to the shape. There's our 5 carbons, and 1, 2, 3 hydrogens. This carbon has 2 bonds, so it needs 2 hydrogens. This carbon has 3 bonds, so it only needs 1. And continuing, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are isomers. And from there, we'll start doing, let's see, we'll draw the one other isomer of C5H12. 1, 2, 3, 4, 5. This is another isomer. So these are the 3 isomers of C5H12. Now on the next page, we'll talk about functional groups and how to represent functional groups in skeletal structures. And functional groups, we've talked about what they are, and 2 of the most important ones are carboxylic acids. Those form weak acids, or those are the weak acids. Those have the COOH group in them. And let's draw, how about 1, 2, 3, 4, 5. We have 5 carbons, and then double bond OH. So if we were to count carbons here, then the first carbon is right here. 2, 3, 4. This molecule has 5 carbons. It has an O and an OH, where typically it is connected to the O, and then the O is bonded to the H. That means each oxygen has 2 bonds. This is our first double bond, which is 2 lines. Now let's go to an alcohol group. And for an alcohol group, it's just OH. 1, let's do 1. Let's start up top. 1, 2, 3, 4, 5, 6. And we might do OH. This point of right next to the O is not a carbon. The first carbon is here, then 2, 3, 4, 5, 6. And again, I'm not being too careful about the exact bond angle. I guess maybe anywhere slightly more than 90 to 120 is fine for these. In fact, these are single bonds, and we'll talk single bonds rotate, double bonds are rigid. I'm trying to think if there are any other functional groups that we need to know about. Well, and the important thing is an H bonded to an O, you do draw, I guess an H bonded to an N. One, let's see, you can draw as well. This is a cool molecule because it kind of looks like a bat, and it has nitrogen bonded to 3 carbons on one chain and 3 carbons in another chain, both of those attached to the nitrogen. For skeletal structures, you don't have to draw all of the pairs of electrons. Remember, for Lewis structures, you do draw all pairs of electrons, but for skeletal structures, they're really a shorthand notation. And if you were to draw the full Lewis structure, then this oxygen has 2 pairs of electrons, this nitrogen has 1 pair of electrons, and these 2 oxygens each have 2 pairs of electrons.